stress, and that the stress concentration will be around the discontinuity of the geometry just around here, and the magnitude of the maximum stress in stress concentration basically taking up this formula. K is the value obtained from the curve, and Tc over J, T is a torque in the structure, J is the geometry, C is also the geometry. J and C are associated with the smaller shaft. Okay, that is the key point in these calculations. If you take out the bigger one in the calculation, then you got the wrong answer. Okay, because the way the people come up with this formula just for predicting the maximum stress, we just follow up the step. And this is one example. We can do it. So that example is 60/30. Okay, so for this one, let me first get the K value and before to move on, because I'm to like to use the space here. So for this case, we have 60D equal to 60 millimeters. A smaller case D is 30 millimeters. And R equal to 8. This is given here. So with the three information, let me go to previous slide and to get the K value here. So here we need to calculate, to get a curve, we need to get the calculate D over D. For this case is 60 divided by 30 equal to 2. And also we need to calculate R over D. And R over D is 8 divided by 30. And that is how much? 2.026, 0.267. Okay, so with the information, pretty much we can predict R over D is 0.20267. So that is about nearby here. 1/3 beyond. So that should be go to here. Let me. Okay, so that should be go here. And then we get the value for 2. So this curve is corresponding to this value. So this is a point. And the K value point to corresponding to that value, that point is about, we can estimate 1.18. Okay, estimation will be good. So K value is 1.18. We take down this value here. And remember the Tc over J, here the tau maximum we have is Tc over J and times K. And here the C is for, remember this one, the C is the radius of the smaller shaft. So here for this case, C is equal to D divided by 2 equal to 15 millimeters. So those are the information we have, and then we turn off the slide and work on the example.
Wait, can we go to the next slide really quick?
Yes. This one.
Okay.
Okay, so for this problem, we'll look at the information here. We're looking for is, let me change the. For this one, we have the allowable stress equal to 45 MPa. And for this case, I can draw the stress concentration. So this is the two shaft, and basically they have the geometry These are R here. So the distribution of the stress around here, that would be something like this. I can schematically draw this. On this cross section, distribution of the stress could be something like this. So this value is the tau maximum. And those nonlinear stress wouldn't be able to calculate by hand. So the only way is by prediction. So for this case, the tau maximum must be less than or equal to the allowable stress. Okay, and per our calculation, this one is K times TC over J. So therefore, from here, the K equal to 1.18 multiply TC over J, and we want to calculate the torque, the power. Let me do this one here. The torque we applied, and C equal to, we calculate there is, again, we take up the smallest shaft to, as our the C. So this is the point 0.015 meter, and J is pi over 2.015 meter to the fourth power. This one is less than or equal to 45 times 10 to the 6, and this is the Newton per meter square. Okay. So on this side, everything is converted into the meter and newtons. So by solving for this one, we would obtain the T must be less than or equal to 202.17 Newton meter. So that is the allowable shaft, the torque that can be applied to twist this shaft. And now we want to know is what will be the maximum power be delivered. So again, using the equation, power equal to 2 pi F times T. And we already have the T being calculated, and here the F is the rotation, the speed of the rotation, and in terms of the hertz, and here is 50 hertz. And T is the calculated, T is less than 202.17 Newton meter. So this way, this is less than or equal to 2 pi times 50 times 202.17. And we do the calculation, and this will be 63.5 times 10 to the 3 watts. 63.5 kilowatts. And I don't know the conversion, the unit between the kilowatts and the horsepower, but you've been taking the...
It's 746 watts is the horsepower.
Oh, nice, genius. How do you know? 7.46. 7.46. 635,000. And okay, so this one about.
Oh, that 7.46 is per kilowatt.
Per kilowatt. Oh, okay. So that would be 8, less than 8, 8.5 horsepower. Okay, so I believe this could be the for the Scooby motorcycle. Scooby Doo, you know what I mean? Okay, so that is the power that's too small for drive to drive a car. So that is the last question, last topic we have. In this question, we not only exercise how to find the K and how to predict the maximum stress, and we, one more time, we exercise the design criteria. And then here we exercise the power. This is the equation. And because the topic here is so straightforward, so let me stop here. And so here we finish chapter 3. And the test on Monday, this kind of the stress concentration will not be on the test. And as long as you can finish the homework problems, and you should be fine. And this time the test problems is somehow similar to the homework problems. Okay, and so encourage you to try to complete the homework and understand and how to finish all the single problems in the homework. And the gear systems are important in these chapters, so I can tell you the gear system will be on the test. So that means to test you, do you know the two relations, power translation and the angle of rotation, that kind of transmission to the gear set. So that is the one that will be on the test. Okay. Our tutors, Matthew, don't know. I didn't give him these test problems. Yeah, so he will try his best. But I provide him our homework, so he should be able to help you more on the homework. Okay. Any questions? The general questions about chapter 3? If no, then we can move on to the chapter 4. You can see here our page is pretty fast, but I try to give you as many as possible. Chapter 4 is about the bending. The chapter 4 we talk about is about the bending, and bending right now we have talked about is the axial loading. If this is a bar, if we apply the axial loading, and that is chapter 2, and chapter 3 is torsion, and chapter 4 is about the bending. Bending, the loading is like this. Okay, bend over. And in particular, chapter 4 we talk about is the pure bending. Pure bending, that means in the certain portion of a structure, the bending reaction at every single cross-section is constant. This is called a pure bending. So that means for this example, if we can analyze, for simplicity, the two hands are as a support, and here is the loading. So, for example, here is 80 pounds. I don't believe that is 80 pounds. This could be 300 pounds on each. Okay. So that is a load, and that's the hand. And later I will show you how to calculate the reaction of the bending at every single cross-section. But I can tell you at this moment, in portion C, between C and D, in this portion, the bending reaction at every single cross-section is constant. For this example, is 960. So in this portion, we say this structure CD, the segment CD is under pure bending, and the magnitude is 960 everywhere. This pure bending will give us the simple way to analyze the problem. And once we learn the pure bending, and then follow up, we can extend the techniques to study the bending of non-constant distributions. Okay. So that is our stories here, and the bending basically is this. And from now on, we talk about these being on the pure bending. Basically, we will take up this model. So assuming we just apply the moment at the two ends, so in this way, that will give us the pure bending scenario, okay? And again, you should remind yourself, this portion, this is a generic model, and this could be a portion of the whole structure like this, or more complicated. Okay, so again, this is our generic model. We're going to use this model to develop the necessary formulas for describing this kind of loading situations. The bending may also occur in other structures. And for this example, you can see this is kind of the C clamp. And for example, here, if we have something to rebel this kind of clamp, so for example, that will produce certain reaction here. So in terms of this loading applied to this surface, then we can look at what will be the reaction, for example, at the cross-section here. And if we take a free body diagram on the upper portion to expose this cross section here, then you can tell by force equilibrium in the y direction, this is a reaction force in magnitude equal to 150. And also in taking the moment equilibrium, you can see this pair of the force will produce a net rotation counterclockwise. This moment must be balanced by a reaction bending inside this reaction. So that means this is the counterbalanced reaction, and that will give to the magnitude will be equal to the force multiplied with the arm and 750. This is a traditional statics. Should be very easy, straightforward. Okay. So for this case, you can tell that bending will also occur in this portion. And again, if we further study the taking other cross section, for example here, this level or this level, anywhere, you can tell, doesn't matter how we pick our cross section, this bending will be constant everywhere. If you take a little bit more free body diagram, you can quickly verify the bending on every single cross section here, 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 here will be equal to this number. So that means in this portion, this one, again, is under the pure bending case. Okay, so this is another example. We will be later on to apply the techniques in this chapter to study the stress in this portion. And the stress that will induce by the bending is called the bending stress. Okay, and that is just a special name. So sometimes you will see the bending stress. And what is the bending stress? Basically, that is a stress induced by pure bending or by bending. Okay, and later once we get into the formulation, you will see quickly. Actually, bending stress is one kind of the normal stress. And that is our topic in this case. This is another example, and this is a beam, and one side is climbed against the wall. So basically, this is a cantilever beam. We call it cantilever beam. Okay, so that is the name. And again, here, if we take a cross section, the section is placed by a distance x from the free end here. So again, if here we take the free body diagrams to calculate the reactions at this cross section, the first one we take the force equilibrium in y direction. So this is a reaction in magnitude equal to p, which is applied. And also, this pair of the force will produce a change of the rotation, the net change of the rotation counterclockwise. So on this cross section, we must have the counterbalance, which means reaction bending and that magnitude equal to P times X. This is another example to produce bending in the beam. For this example, let me ask you, the bending is constant everywhere in the cross section, or it's changing? Changing. Actually, you can see the magnitude of the bending equal to P times X. So the magnitude of the bending on the cross section here will be different from here. Actually, the bending at this cross section which will be bigger. So for this case, for the cantilever beam, the bending on the section is varying. So this will be the topic not to discuss in this chapter, but will be in the following up the chapters. For this case, this is not a pure bending scenario, not, okay? So, but here kind of show you we could have this kind of scenario. And again, the techniques we learned in this chapter will be able to solve for the problems of this kind in the futures. So that is the third example for producing bending. And now we come to our the assumptions, some basic definitions and assumptions for these chapters. If we consider, again, we consider the pure bending is this. We consider a beam, and we apply the bending at the two free ends. So we bend over like this or like this, then the whole things will be under pure bending, which means at every single cross section, the bending direction will be the same in magnitude. And furthermore, and here you can see the model I use is very thin, the aspect ratio is very thin, right? So if you think that is a little bit fat, like this one, and here we want to assume to eliminate unnecessary the modeling. So here we assume that the bending actually applied on the surface of the symmetry. So that means